The next item we're going to look at is the continuity equation. And so this is something that's used often in electronics, semiconductor physics, and as we'll see later, electromagnetics. The basic idea here is we're considering charge conservation, and we're saying that a net outward current through some closed surface has to be equal to the time rate of decrease of charge within the volume. So we're basically saying if we have a current coming out of a surface, then the charge enclosed in the volume has to be decreasing in order to essentially provide that current. So we can write this in terms of an equation. We can say that our current out of the surface is equal to the closed surface integral of j dot ds, and we're saying that that also has to be equal to the time rate of decrease of charge within the volume. So that's going to be negative d of our q enclosed with respect to t. All right, so now we're going to sort of adjust this equation a little bit. So let's start with this middle expression here, and let's apply our divergence theorem. So applying divergence theorem, we can say that this closed surface integral of j dot ds is just equal to the volume integral of our divergence of j. And so that's going to be dv. And so remember that the volume is the volume enclosed by that closed surface S. All right, so now let's adjust this right side of our equation as well. And so if we're talking about Q enclosed, so let's see, we have negative derivative of Q enclosed with respect to T. So I'm going to leave this d dt out front, and remember we can define our Q enclosed as the volume integral of our volume charge density. So we can say Q enclosed is the volume integral of rho v dv. So now I'm going to move this d dt inside, and so doing that, I'm going to make it a partial derivative of our rho v. So we have then negative the volume integral of the partial of our volume charge density with respect to t times dv, so our differential volume. So now we can sort of compare these two adjusted forms, and we see we have two volume integrals. And of course we can think about moving this negative sign inside, so let me actually just do that for clarity. So let's move this negative sign in here. And so we can just compare the two integrands then. So we have our del dot j, and we have this negative partial derivative. And so of course these two integrals are equal to one another. So we just, from comparison then, can say that the divergence of our current density j is equal to negative partial of rho v with respect to t. And so this is our continuity equation. And so we could sort of consider a special case of this continuity equation, and we could say what happens for steady state currents. So of course steady state currents, no change over time, or not necessarily no change over time. So for AC steady state, of course, we have change over time, but it's sort of that predictable change based on what our input is. And so this is what we're considering sort of in basic circuit analysis. So for steady state currents then, of course, the change in that charge density over time is going to be 0. And so that equals the divergence of our j, so that equals 0. And so the reason for that is because, of course, everything that is going out is also sort of coming in, it's being replenished. And so to sort of write that explicitly, we can say our total charge leaving a volume is equal to the total charge entering the volume. And so that might sound kind of familiar. So something we used in basic circuit analysis that's similar to that is, of course, our Kirchhoff's current law. So this is sort of a basic, sort of foundational equation for Kirchhoff's current law, which we can apply for steady state conditions.